Welcome to everyone on another show on today's show. Thank you so much to Liberty once again for sponsoring the show. And you haven't done it yet, please do download the Tenfold education app. That is true. It is a Tuesday and you are sitting with me, Tobi Lenkosi, and we will be doing physical sciences revision for grade 12. We will be looking at paper number 1 and paper number 2. Now, I know it is a bit critical time now today. I know some of you guys have gotten your results and you can probably now see where your strengths lie. Now, remember guys, if you are better at chemistry, make sure you get 150 out of 150 for paper number 2. If your strength is on physical sciences, which is paper number 1, you must make sure that you ace your first paper. Get 150 over 150. Another piece of advice that I can give you guys, when you are going through your work and you are studying, make sure you always, this is what I always tell my kids, you can start with what you're strongest at and then use all the other remaining time to focus on what you're not so good at. But I always say, if you are strong with work, energy, and power, get full marks for that section. It really does build up for you to getting a distinction, and as well as for paper number 1 and paper number 2. So without wasting any more time, I want us to start looking at today's question. So the first question I have is from Junior Chauke, and he sent us a paper number 1 question, and this is question number 5. And this is a work, energy, and power question. Before starting this question, I want to take you back to where the foundation of work, energy, and power comes from. Work, energy, and power starts from grade 11 when we first do vector diagrams and then we do Newton's laws and all that stuff. If you're having a little bit of a problem on how to work with work, energy, and power, make sure that you take your grade 11 books and then you sit down with that and you take it from there. Why does Tobile say this? Because number 1, you have to know how to draw a free body diagram. You need to know how to draw vectors. And then if you have that sorted out and you know how to find your equation from your free body diagram, then work, energy, and power will be easy peasy. Remember, the nice thing about physics, you do get a formula sheet, but from the diagrams, you need to know how to work or maneuver your way around. So let's read what today's question says. It says, the track for a motorbike race consists of a straight horizontal section that is 800 meters long. Now, what I always tell my kids, if you are reading an exam paper during the exam session, I like using a highlighter or some color. So you actually highlight all the important information that you're given. Why is that? Sometimes when we are reading, we get so excited to think what the question paper is actually asking and not what they're actually asking, and we don't actually read all the nitty-gritties. Make sure you highlight all the information. If really needs be, write it on the side of your question paper. I've got my distance, I've got my velocity, I've got my time, and so forth, and then you are able to work out the problem. So as we move along, I'm going to show you how I do it. So we have the track, which is 800 meters long. Remember, in physics, when we talk distance, it must be in meters. If it was not in meters, we would have first converted it. So here's the diagram that we're given. We are told that a participant, such as the one in the picture above, rides at a certain average speed, and he completes the 800-meter course in 75 seconds. Now, we need to know, if we have to run 800 meters and it takes us 75 seconds to complete it, we must have had a speed in which we run. That is why we can say people can run the 100 meter in 9.4 seconds, right? We have distance, we have time, we are able to then find the speed in which that person has traveled. So now, reading my head, I've got one unknown. Now, to maintain the speed, a constant driving force of 200 newtons acts on the motorbike. Just by mere looking at this picture, I can see that this person is moving this side, so the force applied will be 200 newtons on that side. 5.1 says, calculate the average power developed by the motorbike for this motion. Now, everything that I have, let me just change color. I have distance, I've got time in seconds, I've got force, which is 250 newtons. So then, if you didn't know, you go to your formula sheet and you find an equation that allows you to use any of those. So I'm going to do it the long way around. This is 5.1. We were given our distance, which was 800 meters. We were told that it took a time of 75 seconds. We were also told that we have a driving force, I'm just going to say FD for driving force, of 240 newtons. I then have to go to my formula sheet and find a formula that requires me, let me just see what they wanted us to find again. We must calculate the average power. We must calculate the power based on what we are given. So I'm going to show you various ways on how you can do it. The first way I would do it, if you know average AVE, remember I can say my distance over my time. My distance, they told me it is an 800 meter course. that he completed in 75 seconds. I'm going to use that on my calculator. So I've got 800 over 75. Let's see what I get there. I get 10.67, remember 3 to 2 decimal places. If the third number is 5 or greater, then it will change the second number to the next number. So then I get 10.67. Remember, the SI unit for velocity is then meters per second to the exponent 1. But there's a power. Now that I've got my velocity, I can therefore say my power average is equal to the force that the object has multiplied by the average velocity. The force that the motorbike has, we were told, is 240. The average velocity we got was 10.67. I'm going to go back to my calculator. I'm going to just take it as it is, multiply that by 240. Remember to always round off your final answer. So I'm going to say 2560 is my final answer. 2560. Remember, the SI unit for power is a capital watt. Small watt is weight. So that is the first option that you could have done. I'm going to say or here. I'm using again all this information that I'm given. Or you could have said, go straight into it. You could have said power is equal to the work done over the time taken. Now remember, taking it back from work, when we break up work, work is the force of the object multiplied by the distance traveled multiplied by cos theta. And that is all over change in time. Now we are told that the force that this motorbike has a force of 240, that's the driving force. Delta x is my distance. They did say it's on a horizontal straight line. And he completed an 800-meter race. I'm going to say cos of 0, which is 1. Remember, if we say cos of 180, that then means we are talking about friction. But in this case, they didn't say anything. Delta time, it took him 75 seconds, to complete the course. I'm going to go back to my calculator and I'm going to plug it in exactly as it is. So remember, I always like putting my things in brackets. Otherwise, your calculator is going to do BODMAS. 800. Cos of 0 is 1. So I'm not going to add it there. Just close my bracket there. And at the bottom, I've got 75 seconds. That's how long it took him. And I get 276. Let me just do this one quickly. Let me just put the cos there. Let me start it again. I don't know where I pressed there. I've got 240. I've got 800 meters. Let's put the cos of 0. And I have 75 at the bottom. There we are. We've got 2560 again, which is power. 2560. The SI unit for power is watt. Remember, you cannot be forgetting your SI units, especially not in grade 12. Or the last method, you could have done it. You could have used, again, I could have said my average velocity. Remember, if you've got distance and you've got time, then you can find what is required. I could have said 800 because that's the distance traveled over the time of 75. I'm not going to work this out. This is exactly as this one. I just want to show you how it follows through. So we have 10.67 meters per second to the exponent y. That is the SI unit for average power. By using my velocity, my average velocity, I'm able to take the work done is equal to the force of the object multiplied by the distance traveled and then cos of theta. Now, I want you guys to think about this logically. If it takes us 10.67 meters per second, so for every, let me just make a little asterisk here, for every 1 second, we are able to complete 10.67 meters. Remember in physics, meters per second. 1 second, we cover 10.67. But it's probably like Usain Bolt kind of times, but yes, so you could have used that law of physics and taken it off by that, saying that the force is 240. My distance per second is the 10.67, and then I've got cos of 0. I'm going to take that to my calculator as well. Make sure that you put everything around brackets. That's 240. I'm going to have 10.67 and cos of 0. And then again, I get the 256.0. 25. So So there are truly a million ways to kill a cat in physical sciences. 2560.8 joules. Now, what you could have done, you could have used any of these problems to actually solve it out, but what did I do? I read my instructions, I looked at what I had, and then if you really are struggling with it, go to your formula sheet and then say, okay, I need to find the average power, but this is what I have. Then you work with what you have and then work backwards. However, if you look at method number 1, if you look at this method and you look at this method, it is a bit risky because if this one is not correct and this one is not correct, then you filling in this one is a bit, not on the good side. But I do know if you, whatever answer you got wrong here, if you were to substitute it correctly here, that's continuous assessment. So you would still get your marks there. So if you know that you're not really sure or you don't want to make mistakes, don't rather use formulas where you have to use one, get an answer, use that answer, move on to the next one. Or if you do have time in your exam, my darlings, I would say use 2 formulas and see if you actually get the same answer. Because if you do get the same answer, then we are truly then good to go. But this is then how we would have answered problem number 5.1. Let's just move to the next one again. The story here continues. And it says now, okay, we calculated that one. So now we have another person who practices on the same motorbike on a track with an incline. Now, obviously, if somebody is on a flat surface and they are running, the force that they're running on a flat surface or on a horizontal surface does not really use the same amount of force if it's on an incline. Then on an incline, you need or require a little bit more work done actually to get on top of the hill. So really put that in the back of your mind. So we have this person on a track with an incline. He starts from rest. Now, start looking at physics terminologies. If anything is on rest, it means that the initial velocity is 0 meters per second. Now, one other thing that examiners like doing, they like using physics genre. Remember, physics and chemistry is a language on its own, right? So when they talk about something did not have a velocity, they just say at rest, or it was standing still, right? So you must look at the little words that they use. If something was at rest, it does not have an initial velocity. If something was dropped, it doesn't have initial velocity. But if something was thrown, if something was pushed, that we can then say there is initial velocity because that object did not move on its free will. It actually had a little bit of some support to actually get it moving. So from rest, I can already know that my initial velocity is then 0. Here's the diagram that I have. I know that I've got height and I've got distance. Already just by mere looking at this, if ever you were asked to calculate something else, you can actually easily use theorem of Pythagoras. But let's continue to read what it says. It says the total frictional force acting on the motorbike is 294 newtons. Now remember, if the motorbike is going upwards, we know that frictional force opposes the motion, and the frictional force that we have here is 294 newtons. Another thing, my dollies, you must know how to define frictional force. They will ask you. And the combined mass of the motorbike, of the rider and the motorbike, is 300 kilograms. The mass of both of them is correct. Remember, when we talk about mass, we talk about kilograms and not in grams. And the average driving force on the motorcycle as it goes up the incline is now 350. Just want to take you back here. On the flat surface, we had a driving force of 240, but now on an incline, it then becomes 350. Now they continue to tell us we must consider the motorbike and the rider as a single system. Now this is very crucial to why they're saying a single system, because they could easily say, calculate the speed of the rider, right? Because they are 2 separate objects, but now that the rider is on top of the bike, we can then move it as one system. For an example, if I was to put Bali on my back and I was going on a scale, the scale wouldn't say Tobile weighs 55 and Bali weighs 35. They would give us one weight, right, or mass. It's the same thing when we talk about the motorbike and the person. We are talking about them as one complete system. Keep that in mind. Let's continue. Now 5.2 says we must draw a labeled free body diagram for the motorbike rider system on the incline. With questions like this, my darling, the mark allocation will tell you how many forces you have. 4 marks means 4 forces. We must look at this rider. Let me just erase all of this and then let's just take it from here. Take away all of that. There. Let's see. We have the rider that is going up. He has a force applied, that's the 350. We were told that friction, which is opposing motion, they told us that we have friction in the opposite direction, which is 294. Now, we do know that all objects have a normal force, which is perpendicular to the surface. And we also know that everything has got gravity, the force of gravity. Remember, if you do FG, you don't have to draw FG's components. 4 forces for 4 marks. However, it is a free body diagram, which means I need to have a dot instead of the actual picture. And this is 5.2. I want to elaborate a little bit further on this. In grade 11, you were taught how to draw a vector diagram, whereby you use a square. Now in matric, we have moved you guys over and we say you must draw a free body diagram, which means the object or the block you used to draw in grade 11 turns into a little dot or a circle, right? And then from that circle, that is then where you draw all your vectors. Do not confuse a vector diagram with a free body diagram. You must make sure you know the difference and you start practicing. The only difference is the one has a square and the one has a circle. So this is how I'm going to do it. I'm going to draw my square. Now remember, it is on an incline. If you are pretty bad at drawing it on an incline, I would say draw your incline like this and then draw your normal force, which is F of n. Remember to always name it. I'm going to have my frictional force moving in this direction. I'm going to have my force, the driving force. Remember, can you see it's at an incline? We were not giving an angle, but this shows that it's on an incline. I'm now going to take this away. Remember, we've got the force of gravity, which must go straight down, which is Fg. I just want to show you the wrong version that some people do. Remember, let me just actually draw a dot. Let me not take shortcuts. If you draw a system that is like this, if this is Fd, you've got your normal force going up, and then you've got that, and then you've got your Fg going down. This number 1 and number 2 is completely different things. The examiner wants to see that this is at an angle and your FD is actually moving up at an angle. Friction is moving down at an angle. This means it's on a flat horizontal surface. Remember, you do want to get all your marks and you do not want to make the examiners think you do not know what is going on. So that is then my free body diagram. You get a mark for naming all the diagrams and actually having the correct vectors around them. Let's see what the next question says. Now it says, state the work energy theorem in words, and that is then only for 2 marks. I want to take this back a little bit. If you have to state something, if you have to define a law, it means you are not explaining what you understand or what you think is going to happen or is happening. When you state and define something, it must always be the same. Those are the principles, laws, and phenomena of physics that will never ever change. If I ask Mbali, oh Mbali, please explain what you think about the color red. Mbali can tell me anything. Oh, Top's blood is red and all that stuff. That is her explanation. But if we have to define something, it's something that remains like that and does not change. So this means you must know all your theorems, your definitions and principles off by heart. I always say this, you cannot fail because you were lazy to read. My advice to you guys when you are writing definitions, if ever you're working with any work, energy and power problem, when you are practicing, start with the definition, look at the formula. If you do kind of forget the definition, go back to your formula and see what the formula is. I'm going to show you a little trick on how I always remember all my definitions by actually referring back to the formula. So with this one, let's state the work, energy and power theorem first. And this one is 5.3. So the work energy theorem says, I'm going to show you 2 methods on how you could have done it. The net. Now, it's very important you don't say all the, in physics, net is the sum or total of. You don't say all the, we say net or total. All the net work done on an object is equal to the change in the object's kinetic energy. In the object's kinetic energy. Now remember, the examiner wants to see different words. They want to see that you get marks for having certain words, rather, when you are writing this definition. So make sure you have all your terminologies as you need them. Some teachers or some textbooks would have it like this. Make sure you know it and you understand it. The work done on an object by a resultant force. You remember terminology. We don't say the total forces and all that stuff. We are looking for certain terminologies. But resultant force is equal to the change in the object's kinetic energy. And the objects there we are. Now, just going to read it quickly. The work done on an object by a resultant force is equal to the change in the object's kinetic energy. When you're looking at the formula, of the work energy theorem is work net is equal to delta. Remember, in physics, that triangle means change in K. I'm going to take it a little bit further. Work net is, remember, change in kinetic energy is a half mvf squared minus a half mvi squared. Now let's elaborate. How do I remember this? The work done on an object by resultant force, or the total work net done on the object is equal to the change. When we talk about change, we talk about that triangle there, is equal to change in the object's kinetic energy. And this is then how you use your formula in order to get your definition. And if you are truly, truly smart, guys, with all the physics and most of the chemistry, you are actually able to actually just look at the formula and then come up with your definition. So make sure you actually get that right and you do not get that wrong. I think we have one more question to answer. Let's see what the last question says. Ooh, and it's for 6 marks. So we do know there's a lot of calculations there. So then 5.4 says we must use the energy principles to calculate the speed of the motorbike at the end of the 400-meter ride. I'm going to go back to this diagram. Let us look at it, elaborate on it, and then let's see how we're going to figure this out. We are told that we've got a driving force going up. We are covering a certain distance. Now we know if we're talking about work done, we do talk about a certain distance. We've got frictional force in the opposite sides. Now we know that if this is a driving force and this is friction, vectors in opposite directions need to then be subtracted. Another thing we can find from this graph, especially with the energy principle, we've got height, we've got velocity. We were told that our initial velocity is 0. They want to find our final velocity at the end of the 400-meter ramp. So that is number 5.4. So let's see how we're going to answer that one. Now, there's various ways you can probably answer this. I'm very comfortable with using forces and then moving to work energy theorem. If you are not so sure about your forces and you feel comfortable with using just work energy principle, then you're more than welcome in getting it like that. But remember, you have to use the correct physics steps in order to get your final answer. The examiner will not penalize you with what method you have used, but don't take shortcuts and make sure that you show everything on how you actually got your answer. So I'm going to show you one of my methods on how I got it. This is what I do. I love working with forces. So I said, or I would say, I would look at F net. Why would I do this? Because there is a formula that says work net is equal to F net delta X cos theta. Now, if I can find the sum of all the forces, I am then able to find the rest. So work net, now remember, work net, what is working on that object? I just want to redraw this again. Remember, we had our normal force that is moving in that direction. I had my driving force, my FD. I know I had my frictional force in the opposite direction. I had the force of gravity that was moving down. So what is making this object move up? It is then my driving force. What is bringing it down? It is my frictional force. But what else? We have gravity. But FG parallel says, you need to come down. So these are the two forces. I'm going to have FD, which is in one direction. I'm going to subtract friction, and FG parallel because it is then in the opposite direction. Now it's one of two things. You can work FG parallel out separately, or you can put it in one equation. I think just to be safe, let's work it out separately. Remember to always show the examiner how you work it out. FG will be mg, FG parallel, we use sine theta. We use sine theta, and I was given an angle of 0.64. Use 0.64 was the angle that I'm given. And let's see how I get that. So this will be sine of 0.64. The mass of the bike and the person, they said together they are 300. The gravitational acceleration is 9.8, and I'm going to have sine of 0.64. Let's see what my FG is. Remember, if you do it like this, show the examiner where you work it off. Don't work it out in pencil and then just write the answer. You will get a mark for working this somewhere, somehow. So rather write everything so that you are actually follow through with the examiner's memo. So now I get 32.84. Remember, if the third number is 5 or greater, then the next number will then change. I do, though, advise you guys to only round off your final answer. So I'm going to leave it to 2 or 3 decimal places just to be on the safe side. So I'm going to leave it as, I'm going to say 32.8394. Only your final answer, then we can round off to the final, to 2 decimal places. So F net, it is my driving force, FD, because it's moving all the way up. However, I have 2 forces. Force number 1, force number 2 are in the opposite direction. I'm going to subtract FG parallel. I'm going to subtract the force done by friction. My driving force, they told me that going up the incline, it has a force of 350. Subtract by FG parallel is the one that I got right over here, which is 32.8394. I'm going to subtract my friction. I was told that friction opposing the motorbike was 294. Let's see what my F net is. I'm going to put it exactly as it is in my calculator. I'm going to say 350 minus 32.8394, and I'm going to subtract 294. And I get 2316. Now with this one, I can actually move it to 2 decimal places because that is my work net. This is a 0, so it remains 16. So my F net will be 23,16. The SI unit for force is a capital N. A small n is moles, my darlings. It is a capital N. Now I'm going to go back to this formula over here. Now I can say my work net, I have my F net. It talks about the distance traveled and then cos theta. I just calculated my work net. My work net is 23.16. They told me that going up the ramp, he had to complete, on the flat surface, he had to complete 800 meters, but on this one, 450. So that is the distance that he had to travel. So that's 450. And then I'm going to say cos of 0. Remember, we only use cos of 180 when we talk about friction. That is the way we get a negative. So I'm going to say 23.16. I'm going to say 450. Remember to always put it in brackets. Let me just take that one back. And then cos of 0. And then I get 10,422. That'll give me 10,422. Did I have any decimal fractions? No, I'm just going to leave it like that. And remember, the SI unit for work done is then in a capital J, which is joules. But however, they said they want the speed at the top of the hill. I just want to remove all that because I'm going to need more space. I want to write here. Now, remember, we have a formula that says work net is equal to the change in kinetic energy. Remember, we just gave this definition. The examiner is showing you that this is what you need to use. I'm first going to do it the long way around, work net. Now remember, change in kinetic energy, I showed you from the definition. We can say 1 over 2, and I can say mvf squared minus a half mvi squared. Then I'm going to do it the short way around. work net, just so that no one's getting lost. I'm going to take out a half m as my common factor because I've got both of them on the same side. This will be 1 over 2m. I'm left with vf squared minus vi over here. I do have my work net. It's the one I just calculated, which is 10,422. This is 1 over 2. The mass collectively, the scooter, the bike rather, and the person are 300. And I'm looking for my Vf squared minus initial velocity was at rest, so this is then 0. I'm going to say 10,422. Now it's just all about mathematics. So let's see, I don't want to get that one wrong. Let me just move this here. I think it's 150, 300 times 0.5. Yes, that will give me 150. That will give me 150. That is 0, so I'm left with Vf squared. To find my Vf squared, I'm going to divide both sides by 150. 150 with 150 will cancel. I'm left with 150 on this side. Let's see what answer I have here. I'm going to have 10, I can't see here quickly, 10,422. Divide that by 150. And then I get 69.48. I've got 69.48. And on this side, I've got Vf squared. Now, the biggest mistake that you guys do is that they're not looking for velocity squared. They're looking for velocity. So you're going to put this side in a square root. You're going to put this side on a square root. A square root will cancel an exponent according to mathematics. And you're going to have Vf left. Let's see what we get on this side. Just going to take my answer, and I'm going to say 69.48. And we get 833. The third number is a 5, so it'll change the 3 into a 4. We are rounding off to 2 decimal places, which is 8.34. The SI unit for velocity is then meters per second to the exponent number 1. I think that was the last question we had to answer for this one. Yes, this was the last question for our work, energy, and power section. I think that was quite a mouthful. I think maybe let's go for an ad break, and when we come back, I'll see if we can't find paper number 2, where we can do revision on organic chemistry.